Skyscrapers, the titans of city architecture for more than 100 years. From New York's Empire State Building to the incredible Petronas Towers in Kuala Lumpur, skyscrapers dominate urban landscapes across the world. There seems to be no limit to our appetite for super tall buildings, and no boundary to the aspirations of the people who create them. Within such high and crowded structures, the consequences when things go wrong can be catastrophic. But from such terrible events comes knowledge. And with knowledge, the opportunity to improve, shape, refine. Today, every major skyscraper under construction across the world is literally built from disaster. Skyscrapers define the modern age of construction, transforming our cities and the way we live. No other design so readily accommodates the voracious need for space in our urban centres. But there can be a high price for this particular solution to overcrowded city life. Mexico, 1985. The Pino Suarez Towers collapsed in an earthquake. In London in 1968, part of Ronan Point Tower block came crashing down. In 2005, the Torre Windsor skyscraper in Madrid was devastated by fire. And on September the 11th, 2001, the world was changed when New York's World Trade Center was destroyed. 2,500 people died. Earthquake, structural collapse, fire, blast. The four main threats to skyscraper integrity. Threats that the designers of every new skyscraper must strive to combat using strategic planning, radical design, and pioneering technology. One of the very newest skyscrapers under construction is the Federation Tower in the heart of Moscow. Its designers believe that when finished, it'll be the strongest and safest super skyscraper ever built. The chief engineer of this Russian revolution is American Brad Marmsden.
This super high-rise structural steel building hasn't been part of Russia's construction history. I mean, some things just couldn't be done here when we started the project.
Upon completion, the Federation Tower will be the tallest building in Europe at a dizzying 365 meters.
For Russia, at least, it's a unique. It's height, it's technology. We try to do something that was never done before.
With no history of skyscrapers in Russia, the Fed's backers have brought in expertise from around the world, employing construction experts from 20 different countries. They're working 24/7 here at level 56 to complete in record time for 2010. Each story is going up in just 5 days. Russia's dream skyscraper is intended to set a new world standard in strength and safety, avoiding the pitfalls of the past. Early one morning in East London in May 1968, a small gas explosion high up in a tower block was to have huge consequences.
I started walking down Bridgeland Road, and as I stepped off the pavement, the ground shook. But almost instantaneously, there was a loud boom overhead that made me duck.
People have been coming in their thousands to stand in the streets nearby and stare upwards disbelievingly at this great wounded slab of concrete and glass.
What caused people to gaze in disbelief was the astonishing disintegration of one of Britain's most popular housing developments, fallen victim to sudden and profound structural collapse.
A sight like that you'll never ever forget. I don't think you could ever forget anything like that. It's that clear in my mind because it was such a shocking sight. You don't expect a structure of that magnitude to fall the way it did.
The reasons behind the collapse of this London tower block were equally shocking. When Ronan Point collapsed in East London in May 1968, both the authorities and the public were mystified. Ronan Point had been built to a radical construction design known as the large panel system, introduced from Scandinavia, where pre-cast concrete panels were used for multi-storey homes. Initially designed for buildings of 5 stories or less, in Britain the system was for the first time employed to erect taller buildings. A comparatively minor incident had sparked the chain of events that blew the name Ronan Point into the architectural history books.
One of the occupants lit the gas stove in her flat to make a cup of tea. There had been a leak in the gas system overnight and it ignited the gas in the room and caused a big local explosion inside her flat.
This local explosion blew a panel clean out of the tower, but the damage did not stop there.
There was like a very loud crackling noise, and then sections started to fall in on top of themselves. Outer sections was folding down and just ripping off. Others was falling down onto floors below. The weight of it was giving way and that was flopping down. It just felt like a house of cards.
What Ray Hollands was witnessing was a phenomenon described by architects as progressive collapse. Progressive collapse happens when the failure of a small part of a structure leads to the whole building tumbling down on itself. In this case, the gas explosion blew out just one prefabricated wall panel, but it led to the entire destruction of the tower's southeast corner. This progressive collapse at Ronan Point killed 4 people and injured more than 17 of the 260 residents. Immediately afterwards, investigators began to search for the causes of the disaster.
Why should this happen in 1968, in the middle of the 20th century, when we knew we had well over 100 years' experience of building?
Investigators needed to find out how a relatively small internal explosion could cause such sudden and total progressive collapse of the entire corner of this multi-storey building.
There must be something wrong with the construction. Something has been left out. It's either been left out in the design, in the construction, or in the workmanship, putting it all together.
It turned out to be all 3. Investigating engineers found that the structure of Ronan Point relied mainly on gravity, downward pressure, to hold everything together. A force or load going upwards or sideways, as happened when the gas ignited, had simply not been considered. Investigators also found that poor construction in the joints meant the blowout resistance of the whole wall panels was less than that of an ordinary pane of glass in a window.
This here is the dry pack, which is supposed to transmit the load from the panel above to the panel below. This should have gone over the full width of the joint, but as you see here, at best it is only over the inner half.
How many joints have you found in this state?
All of the joints have been in this state. I mean, one of the surprising things is that not a single joint that we've so far exposed has been properly constructed.
The failures exposed at Ronan Point caused a public outcry and led to the introduction of new and much more rigorous building standards.
It changed the rules and regulations that we had to work to, and it still is a big influence today, 40 years on from when it first happened.
The new codes required all new buildings to be able to resist an explosive force of at least 5 pounds per square inch. Tests showed Ronan Point could only resist a blast of 1.8 pounds. As an alternative method of design, any key element of the structure had to be capable of being removed without causing collapse. This was to be achieved by providing alternative load paths.
Engineers wanted to make sure they didn't collapse, and in particular that a relatively small accident affecting just a small part of a building didn't act as the trigger to a complete collapse.
Across Britain, many tower blocks built using the large panel system were demolished, and no new ones were ever built using this method again. New skyscrapers were being built, but now they incorporated the lessons of Ronan Point. The first major skyscraper to be built in London after the Ronan Point disaster was Tower 42, completed in 1980. At 183 metres high, it would remain Britain's tallest skyscraper for 10 years.
Tower 42 is an in situ reinforced concrete building. The structure is monolithic. It's like a tree. It's very, very strong.
To give alternative load paths, Tower 42's engineers designed strong and continuous connections linked by a robust central core. The tower is specifically designed to resist progressive collapse.
The connections here between the beams and the columns have continuity. That means that you can transfer load through them vertically or horizontally. The beams don't just rest on the columns, they are joined up together so that you can transfer load through them. So that if something happens, if an unusual load or a very large load occurs, this building doesn't come apart at the joints.
In 1993, this resistance was well and truly put to the test. A large bomb exploded in London's financial heartland and wreaked havoc, destroying a number of buildings and causing more than £1 billion worth of damage. But amidst the chaos and debris, Tower 42 stood tall. This skyscraper's design to resist progressive collapse saved it from disaster.
This building really didn't get damaged at all by a quite serious bomb blast quite close to it.
20 years after Tower 42, more lessons from Ronan Point were applied in the engineering of London's iconic Swiss Re building, affectionately known as the Gherkin. Here, engineers addressed the issue of alternative load paths by introducing a unique steel structure around the outside of the building, called a diagrid.
The main feature of the structure is this diagonal arrangement of columns around the perimeter, which we call the diagrid. And the structural design is essentially to create a symmetrical, triangulated framework of steel elements, which creates a balanced and robust perimeter. That structure, as well as taking all the gravity, the weight of the building, it also provides for stability against wind loads.
The diagonal grid of the pattern on the structure on the outside face isn't just there to produce an interesting shape or for people to look at. It is the structure, a series of interlocking steel pieces that cross over, carry the load, and they form a tube around the outside of the building, and that is a really strong way to make a tall building stand up.
The Gherkin uses an engineering system called redundancy. This is the duplication of critical components to provide backup or fail-safe, ensuring the safety and reliability of the building as a whole. The Gherkin spreads the load outwards, shifting its weight away from any damage caused in the event of a disaster. Its engineers believe its structural ability to resist progressive collapse is second to none. That is, until this skyscraper is complete. Moscow's Federation Tower, due for completion in 2010, employs not just one alternative load-bearing system to prevent progressive collapse, it has three.
It's a kind of belt and braces approach, which gives what engineers call redundancy, alternative load paths for the load to be carried back to the ground.
The first load-bearing system is a central concrete core, similar to that used in Tower 42.
The way the building works is in the middle of the building you've got the trapezoidal concrete core, which is sort of like a tree trunk that centralizes the whole building and holds the middle part of the building together and holds it up. The core stabilizes the tower from the center.
The second load-bearing system uses a perimeter frame, like the gherkin. But here it is made up of 26 concrete columns reinforced with steel bars, called rebar, on each story, linked by beams to resist side loading.
To make sure that we have vertical continuity in the columns is instead of splicing the bars with an overlap splice, we're actually threading the ends of the bars and screwing on mechanical couplers, creating a very tight, very solid tensile connection for the rebar. So it's almost like this rebar all the way down to the ground is a continuous steel tension rod running through the vertical column.
The vertical columns are securely connected to the concrete floor slabs at every level.
On top of that, we've got some really nicely tied up and closely spaced stirrups that are running across all the slab rebars. So what that does is it makes the joint between the slab and the column very strong and very stiff and very resilient.
And the Federation Tower has a third system to spread the load and thereby prevent progressive collapse. Positioned at 4 levels throughout the building are outriggers, a system of reinforced crisscross concrete beams which reach out from the central core to the perimeter, linking the whole structure together.
The outrigger is spanning out to the perimeter and it runs into the belt truss here. So this truss, these diagonals are making up what's called the belt truss. They span all the way around the building and the outrigger is spanning into this. It hits down on this, the load spreads out through diagonals and into all the columns, all the perimeter columns. So in the case of a catastrophic emergency, if one of these columns happened to be cut off or removed or something during the life of the building, the columns below could hang themselves up through the steel inside the column to this belt truss, and the load could span back through the belt truss either to more columns or even into the outrigger and into the core.
With these 3 systems in place, the Federation Tower promises to be one of the strongest and most stable skyscrapers the world has ever seen. And its strength doesn't just lie above ground, it's incorporated into its very foundations. The Federation Tower is anchored to the ground with 14,000 cubic metres of high-strength concrete. It pours non-stop over 4 days to create a massive anchoring slab. What's more, the pouring took place in the midst of the harsh Moscow winter.
During the early months of this project, we were pouring in minus 38 degrees. That meant that we had to have cocoon situation to keep the concrete warm. The concrete pumps had to be cocooned. The concrete lines had to be traced. But inside the cocoon, we were achieving plus 12.
The foundations have been piled down through 2 layers of rock, filling any voids with concrete.
They had a huge crew of people in here with concrete just coming around the clock pouring, and they keep it wet through additives in the concrete that help it set a little bit slower than normal concrete. They're vibrating it with vibrators all around to make sure the concrete flows freely throughout the whole course of the pour. And what that did was it allowed us to have a very nice, stiff and solid foundation mat to sit on top of all these piles.
Engineered to resist forces exerted from above, from the side and from below, and with its strength reinforced by foundations 20 metres deep, the Fed is a building capable of withstanding almost anything, even, its builders believe, an earthquake. Moscow is not in a seismic zone, but the designers of the Fed are taking no chances. Indeed, engineers have learned a great deal about the construction of skyscrapers from analysing the impact of earthquakes on tall buildings.
The effect of earthquakes on buildings, of course, is one of the few opportunities structural engineers have to test what they've designed virtually to destruction.
But it wasn't until the Mexico City earthquake in 1985 that a discovery was made which would revolutionise the design of our tallest buildings. Earthquakes are one of the greatest natural challenges for the architects and structural engineers who design tall buildings. But it's the lessons learnt from earthquake disaster that inform the design and building of skyscrapers all over the world, even in non-seismic areas. In September 1985, Mexico City was struck by a devastating earthquake that measured a staggering 8.1 on the Richter scale.
Devastation in the heart of one of the most densely populated urban areas on Earth. 30 hours after the 5-minute quake, Mexican authorities...
At least 9,000 people were killed, and tens of thousands more were injured. Over 50,000 buildings were destroyed or seriously damaged. More has been learnt about building construction from this quake than any other.
The 1985 Mexico City earthquake led us to see that the earthquake really does seek out the weakest detail.
One important discovery was the way in which steel multi-story buildings perform in earthquakes. The steel-built 22-story 3-tower Pino Suarez complex collapsed due to column failure. The columns had been made out of steel plates welded together to form a box shape. The earthquake had stressed the side welds of the columns beyond their strength. As a result, the welds were damaged, the steel columns buckled under the load, and the buildings collapsed. The way pieces of steel are connected is vital to maintain what engineers call ductility, or how far they can stretch before they fracture.
Ductility is a measure of how much an element can stretch beyond the point it actually reaches its maximum strength.
Steel constructions can be especially vulnerable at the point of a weld.
Weld metal is intrinsically less ductile than the parent steel material, and if the welded connection isn't a lot stronger than the member that it is connecting to, then it will tend to fail.
It's a lesson being taken to heart 7,000 miles away in Turkey's biggest city, Istanbul. This is a high seismic zone, and it's only recently that skyscraper development has been allowed here. Upon completion, the Diamond of Istanbul will be Turkey's tallest skyscraper, 270 meters high. Like the Federation Tower, the Diamond has a strong concrete central core. But joined to the core, there are 3 towers in the shape of a Y. And controversially, these towers are being built in steel.
This is going to be first steel construction high-rise building in Istanbul. And maybe it will be the highest one in Europe.
Turkish engineers are using a technique called full penetration welding to make sure their steel columns don't rip apart in an earthquake. The Diamond is using specially commissioned 12-meter lengths of Luxembourg steel for its columns. These are positioned one on top of the other, then skillfully joined together with a full penetration weld, as distinct from the side welds used in Mexico. With experts predicting a major earthquake in the next 30 years, there's no room for error.
Burada kolonların birbirlerine eklenmesini, yani bu kaynakları gördüğünüz gibi full penetrasyonlu dediğimiz tam nüfuzetli bir kaynakla eklenmesini görüyorsunuz. Bu şekilde bir bağlantıyla artık biz bu kolonu, alttaki ve üstteki kolonu monolitik bir eleman gibi, tek yekpare bir eleman gibi düşünebiliriz. Bu kaynakların kontrolleri röntgenlerle yapılmakta ve kaynakların kalitesi sağlanmaktadır.
The columns are then attached to beams using a specially designed bolt and plate system known as slip critical jointing. 128 bolts, each one tightened to a tension of 35 tons, connect the beam to the column. The plates sandwiching the beam act like huge washers, providing friction and ensuring that the connection is stronger than the beam itself.
The main purpose of the slip critical connections is to reduce movement in working conditions. That is, there should be no movement because it's a frictional connection.
Both full penetration welding and slip critical jointing were born out of disasters resulting from previous earthquakes. Now, all across the world, buildings are using these methods. But there was another, more surprising lesson learnt from the Mexico City earthquake. It was discovered that when the earth shakes, very tall buildings often remain standing, while their lower level neighbours collapse. The 7th-floor Regis Hotel, one of the oldest low-rise multi-storey buildings in Mexico, was totally destroyed in the 1985 quake.
In this block stood the Regis Hotel, where at 7:20 that morning, the first of 400 guests had been sitting down to breakfast. As both wings collapsed, all but a few perished.
We also heard the Regis, the facade, the front started to fall off, and there was panic everywhere.
But while many comparable, smaller multi-storey buildings fell down, some of the tallest buildings in Mexico City stayed up, undamaged. Torre Latinoamericano at 182 metres, and the Pemex Tower, even taller at 211 metres, were both unscathed.
Contrary to what people might imagine, many of the tallest buildings survived completely intact, whereas some of the mid-height buildings, and indeed some of the low-rise buildings, fully collapsed. And this focused attention on something called the natural frequency of a building.
Natural frequency is the rate which a building vibrates in response to an earthquake. The Torre Latinoamericano and Pemex Tower fared well because they were so tall that their rate of sway was much slower than that of the shaking ground, so they didn't resonate with the ground motions. Their natural frequency was outside the range of the seismic tremors. Engineers now believe that skyscrapers are actually safer in seismic zones than lower multi-storey buildings. That's certainly what the designers of this skyscraper hope. At 225 meters high, the Torre Mayor in Mexico City is Latin America's tallest building. Completed in 2003, it's designed to withstand a mammoth 8.5 earthquake on the Richter scale. Its engineers have enhanced the effect of its natural frequency with technology developed from the US military, dampers. These are like giant car shock absorbers.
The main purpose of a damper is to absorb energy, absorb vibrational energy as a building sways, whether it be in wind or in earthquake. And basically they provide resistance to movement. That is, if there's a fast movement, they produce a lot of force. If there's very slow movement, they provide very little force.
Each damper in the Torre Mayor exerts well over £1 million of force. They were designed to allow the skyscraper to safely absorb a substantial amount of seismic energy, which might otherwise have caused damage or even collapse of the structure. Disasters caused by earthquakes and structural weakness teach architects and builders important lessons in the design of super tall buildings. But it took a totally different kind of disaster to change their approach entirely. The attack on the World Trade Center in 2001, with its devastating loss of life, received more media coverage than any disaster in history. As well as transforming the political landscape, it also changed some of the fundamental principles of skyscraper construction.
It's led people to think much more about performance-based design and actually questioning and challenging what is right and what is wrong in a building, what is safe in respect to this building. I think it's that change in attitude that's certainly been evident from the post 9/11 era that's probably its biggest legacy.
When the Twin Towers were topped out in 1973, they were the tallest skyscrapers in the world, breaking new ground with their radical all-steel tube construction. However, with 9/11, the weaknesses of the design and materials would be fatally exposed. One of the first lessons learnt was that steel structures can be lethal when subject to intense heat. The tower's steel frames were designed without any masonry or concrete cores. Without these, it had very little effective fire protection. With an open plan layout, the fire had total freedom to spread rapidly. The steel beams failed from the intense heat, and without the support provided by these beams, the columns began to buckle. Like Ronan Point, the towers had only one load-bearing path, and with no alternative, the steels could not support the weight of floors above, collapsing onto them. An initial cave-in triggered a disastrous progressive collapse. But even before the towers collapsed, another fatal flaw in modern skyscraper construction was exposed. With their mechanical and electrical systems unprotected against fire and impact, the elevators in the Twin Towers were rendered unusable, and the stairs proved tragically inadequate for evacuation and rescue. Seven years on, work is progressing on rebuilding the World Trade Center site. The first skyscraper to be built at Ground Zero since 9/11 is 7 World Trade Center.
These are the footprints of the original Twin Towers, which are being designed and constructed in the new World Trade Center Memorial. Tower 1, the Freedom Tower, and Towers 2, 3, and 4 are modeled here, and we are in 7 World Trade Center, which is located right here.
7 World Trade Center is a symbol of America's resilience and determination to rebuild and assert itself as a world leader in skyscraper construction.
We learned on 9/11 about the reliability, the importance of reliability and redundancy of systems.
With an emphasis on safety, engineers here are surpassing New York's already stringent building codes.
We had to reinvent the codes to deliver the strongest building ever built.
At 7 World Trade Center, engineers have continued using steel, but crucially, they're employing an advanced protective coating to safeguard it from fire.
Now, this building fireproofing system, unlike most common fireproofing systems, is cementitious in nature. It has a cement content to it. And it also has a much greater adhesion to the steel and a cohesion within itself. And it's, as you can see, it doesn't compress. So it's much stronger than common fireproofing. And the intention is to provide protection to the structure. It is very important that the fireproofing remain on the steel under emergency circumstances.
When Madrid's Torre Windsor skyscraper was gutted by fire in 2005, the steel structure, some of which had a similar fire-resistant coating, remained standing in spite of the intense heat and the fire blazing for a full 24 hours. The Torre Windsor had a reinforced concrete central core, able to resist the fire, which saved the skyscraper from collapse. It's the concrete core at 7 World Trade Center, with its 2-foot thick walls, which is central to the idea of safety.
The center core is like the spinal column, supporting all of the other elements in the body, and this must be protected, as does the spinal column protect the nerves within the column. And so the reinforced concrete core houses and protects the essential elements of the building.
The designers behind 7 World Trade Center are determined that never again should people be trapped in a damaged tower with no means of getting out.
What you have to create is a building in what you can get out all the people that they are working on the building in a safe way to get them out, and then the building to have the minimal amount of damages.
Here, the essential escape routes of elevators and staircases are engineered within the reinforced core to protect them from failure and provide a protected passage for people to evacuate quickly and safely. They exceed even the tough new building regulations introduced in New York post 9/11.
The stairs are 1 foot wider than required by code. And the reason for that is that we wanted the ability for people to be able to walk down one side and someone else to walk down the other. So 2 people to walk side by side. The code requirements had the stairs much tighter than that and did not enable people to walk side by side or for there to be a counterflow of traffic. Some people going down the stair, perhaps emergency responders coming in the opposite direction.
With wide landings acting as refuge areas, people who can't evacuate immediately can wait, free of further danger, for the rescue services. The core also provides protection for the fire suppression system to mitigate against an interruption to the water supply in the event of a disaster.
Not only are they protected, but we have redundancy. We have one in each of the 2 stairs, and the sprinklers are hooked up to both of them. So in the event of a failure in this particular riser, there's never more than 1 floor without sprinkler protection.
As a direct result of the events of 9/11, engineers at 7 World Trade Center have rewritten safety standards that are now being adopted and surpassed all over the world. Since 9/11, engineers are using every technique at their disposal to future-proof their skyscrapers against disaster. In Moscow, those behind the new Federation Tower are determined that its design and construction will enable it to withstand any threat from any quarter.
Nobody ever thought that airplanes would crash into a building. Nobody ever tried to think about what would happen if all of the building's columns were simultaneously impacted, removing all the fireproofing that was on them, and then melted by an incredibly hot fire.
At the Fed, a state-of-the-art blast-proof facade envelops the building from top to bottom.
Not like any other. Small missile impacts and large missile impacts, the laminated units, glass units on the building are designed to absorb the impact of those missiles, but also to not become disengaged from the metal framing that holds them on the building.
Конструкторам было сделано техническое задание, было сделано предположение, что башня должна быть недосягаема для воздушных атак. Для этого конструировалось таким образом, чтобы выбивание как минимум одной колонны, соответственно, путем попадания любого летательного аппарата, никоим образом цельность башни не нарушала. В этом же контексте мы предположили, что в ближайшее время высотное здание и безопасность, как 2 слова, должны стать словами синонимными.
And the strongest card in the Fed's safety hand? Concrete. But no ordinary concrete. Specially designed super-strength grade 90 concrete. Capable of withstanding a terrifying impact of up to 1,200 kilonewtons.
The formula and the final concrete is extremely strong. And that's why to produce it, we built special factory. We use special laboratories who control the technology. We train the contractor to work with this concrete. It's extremely important and it's extremely fine-tuned job.
The steel encased inside this concrete will not suffer the same fate as the Twin Towers, one of which came down within 56 minutes of the fire catching hold. A central core with 1 metre thick walls of this super-strength concrete will provide ultimate strength against impact, as well as superb fire protection.
The high-strength concrete, they're very thick. They're sort of like a sink for heat. And if you have such a huge volume of concrete where there's a fire next to it, it's better than having a very small volume of concrete. So the concrete would raise in temperature very slowly because it takes such a long time to elevate the temperature of concrete, of this much concrete.
This fortress in the sky is designed to be fire resistant for 4 hours at a blistering 1,200 degrees Fahrenheit. And the Federation Tower is aiming to rewrite the rulebooks on emergency evacuation. Whereas once it was don't use in the event of an emergency, a revolutionary twin elevator system encased within the fireproof core, runs 2 carriages per shaft. These are designed to be used in an emergency and ensure people can evacuate quickly and safely.
9/11 changed the thinking in the elevator business, how to bring the people safe down and evacuate them, not to make the people nervous and not to say you have to take the steps. No, you can take the elevators.
The stairs are also housed within the reinforced core to provide a clear escape route, free from fire and debris. The access to these stairwells is protected by a drencher system, which acts as a water curtain.
Предназначен для того, чтобы задержать данное проникновение огня или дыма в данный путь эвакуации.
And for those who can't escape immediately, there are refuge areas located on the outrigger floors to protect them until help arrives.
The idea of the refuge floor is to give a few floors throughout the building, throughout the height of the building, that people can go and wait for the fire department to get them. So the fire department can actually use a couple of very well protected elevators to come to these floors and bring them back down. Whereas in the World Trade Center, the firefighters were running up the stairs all the way up 100 floors of stairs to try to rescue, as many people as they could. And as well, you can see this is a great place to put it because it's very structurally sound and just very safe.
All skyscraper designers now aim to create buildings that remain strong and stable under any condition, capable of resisting earthquake, fire, blast, or structural collapse. Some aspire even further, taking on what is arguably the most difficult challenge: how to overcome finite energy reserves in the creation and maintenance of super tall buildings.
Super tall buildings have the advantage of being above everything else around it, so they have greater exposure to solar radiation that can be converted into power. But they also have a density that allows you to employ technologies that would not otherwise be cost effective if the building was more distributed and you didn't have that density of space.
With wind turbines, solar energy, and a unique water-cooled air conditioning system, the architects of the Pearl River Tower in China, due for completion in 2010, aim to make it among the most energy-efficient super tall buildings in the world.
We look at how buildings can reduce their reliance on the city's electrical grid. We look to reduce the amount of water that they consume. We also look to take energy that is inside the buildings and recapture that energy and reuse it over and over again.
In Dubai, the proposed 322-metre high Burj Al Taka skyscraper would be entirely energy self-sufficient. Power would come from a 60-metre wind turbine on the tower's roof, from hydrogen extracted from seawater, and from 15,000 square metres of solar panels. In what would be a unique engineering feat, in Moscow and Dubai, there are plans for rotating towers entirely powered by giant wind turbines situated between each of 78 separately rotating floors. Engineering ambition knows no bounds. The Burj Dubai is the world's first mega high-rise. Already at 700 metres, it is the world's tallest structure. On completion in September 2009, it will be nearly 1 kilometre high.
Large man-made structures help to define civilizations. The Egyptians had pyramids. We have our super tall buildings. These buildings will last long beyond us. They will be what we leave behind.
接下来，当性命垂危、生死存亡全系于一通电话的关键时刻，他们是救援行动第一线的抢救部队，急救现场。接着播出。